Welcome back to the You Can Do TV channel.
Experience the energy at Sarstal Askoval, where electric arc furnaces transform scrap metal into versatile steel products. Each furnace can operate continuously for long periods without interruption. The 4 electric arc furnaces handle large loads efficiently, melting diverse raw materials into molten steel. Scrap from multiple sources can be unified into a single high-quality batch. Once melted, steel flows directly into continuous casting machines, forming billets, blooms, or rounds, depending on the required product. Continuous casting ensures that each piece maintains precise dimensions. The process ensures uniformity and minimizes waste. The team's precision in controlling temperature and chemical composition is critical for downstream quality. Each casting sequence is carefully monitored to maintain consistent dimensions and properties. Automated sensors constantly track temperature and chemical balance. Billets produced are prepared for rolling or further processing, with blooms and rounds directed to specialized production lines. It's a little mind-boggling how much energy is harnessed in such a compact operation. Environmental controls filter emissions and recover energy efficiently. Continuous monitoring systems check for deviations in steel composition, guaranteeing the final product meets specifications. Operators coordinate with automated systems to adjust furnace input and casting speed seamlessly. The result is steel that is ready for construction, manufacturing, or further transformation into finished products. This combination of automation, skilled personnel, and advanced furnaces demonstrates how modern steelmaking achieves both flexibility and quality. Sarstal Askoval proves that even complex, high-temperature processes can be executed with remarkable control and consistency. Every step is designed to maximize quality while minimizing waste. Operators guide heavy machines to craft high-strength bolts and nuts with unmatched care at Walter Hasenkamper-Schrauben and Modern GmbH. Each raw blank is selected and prepared for machining, ensuring uniform material properties. Operators guide the heavy-duty lathes and thread-rolling machines with exacting attention, keeping every component aligned. The blanks undergo turning to shape threads and heads, followed by heat treatment to enhance tensile strength. Nuts and specialized screws receive thread cutting or rolling, achieving tight tolerances required in power plants, shipbuilding, and petrochemical installations. Seeing these machines tackle massive steel blanks with such control is impressive, almost like the metal is obedient. Quality checks at multiple stages confirm dimensions, thread pitch, and surface finish. Even the smallest custom order is handled with the same level of care, showing no compromise. The finished fasteners are stored or shipped, ready to secure structures where failure is not an option. Production emphasizes precision, repeatability, and safety, reflecting decades of investment in machinery and quality assurance. Each fastener leaving the factory is a small testament to engineering discipline and reliability. For decades, the production of Morse taper shank twist drills has blended long-held workshop experience with updated machining methods, creating tools that stay reliable across countless industrial jobs. At this facility, each drill bit with a Morse taper shank is formed through a sequence designed for strength in tough drilling conditions. That toughness really shows once the steel starts taking on its early shape. The steel blanks for these bits move through stages that give them both cutting efficiency and stable taper fit. To prepare the bar for forging, operators feed the material into the rolling forged machine, allowing controlled pressure to size the stock for the intended drill diameter. The first action focuses on shaping the tapered shank area to handle torque during heavy drilling. Feels like this step carries more force than you'd expect for a tool this size. After forging, the bar is cut and transferred for tip preparation. Cutting the tips sets the rough geometry, making room for later grinding to bring proper sharpness. To prepare the bar for forging, operators feed the material into the rolling forged machine, allowing controlled pressure to size the stock for the intended drill diameter. The first action focuses on shaping the tapered shank area to handle torque during heavy drilling. Feels like this step carries more force than you'd expect for a tool this size. After forging, the bar is cut and transferred for tip preparation. Cutting the tips sets the rough geometry, making room for later grinding to bring proper sharpness. Shagging removes excess material along the body, improving chip flow. Polishing reduces friction on the flutes, and the shine at this stage feels like a preview of how cleanly it will cut through steel. Heat treatment increases hardness, helping the bit stay sharp under load. Accurate cylindrical grinding on the shank and edge gives the taper its mating quality, while final grinding on the point completes its cutting geometry. Rolling marks identify specifications, and nitriding adds a surface layer for durability. A thin layer can make such a big difference in wear resistance. These Morse taper drills range from 5 mm to 100 mm in diameter. The method here is more economical than fully ground versions, while still delivering consistent performance. Didn't expect the size range to stay this stable across so many steps. Heavy-duty Howden screw compressors at SCS Screw Compressor Specialist go through a detailed repair journey that restores their industrial performance. Every component has a specific lifespan, and knowing which to replace is crucial for long-term reliability. The first task involves disassembling the compressor, separating the casing and rotor assemblies to access every internal component. That rotor looks like it could tip anyone over, but the team handles it with controlled power. Aligning rotors with such tight tolerances requires a combination of skill and patience. Bearings, shafts, seals, and timing components are all examined for wear or damage, with precision measurement tools ensuring tolerances are exact. Components failing inspection are refurbished or replaced, guaranteeing the unit will perform like new. Next, the rotors undergo cleaning and polishing, removing deposits and restoring smooth surfaces. Cleaning alone can improve efficiency by several percentage points in operational output. It's fascinating how the rotors align perfectly after this stage, showing engineering hidden behind brute force. Any minor deformities are corrected on grinding machines to meet Howden specifications. Casings are sandblasted and coated to prevent corrosion, while seals are carefully fitted to maintain airtight operation under high pressure. A poorly seated seal can reduce compressor efficiency and cause premature failure. The way these heavy parts come together feels like a game of mechanical strategy. Every step is checked twice to ensure the unit will run without vibration. Reassembly follows, with technicians aligning rotors and bearings precisely to avoid vibration and ensure smooth operation. Rotor alignment is measured in microns, highlighting the precision needed in industrial repair. Fine adjustments are made to clearances, confirming adherence to manufacturer standards. Electrical and lubrication systems are inspected, flushed, and replaced as needed, ensuring the compressor functions safely and efficiently. That torque on each fastener looks tougher than the machine itself. Functional testing simulates real operational conditions, verifying airflow, pressure, and overall performance. Documentation is updated, and the unit is cleaned, labeled, and prepared for shipment. The coordination of raw strength and exacting skill is oddly satisfying. Even replacing a small sensor can have a big impact on operational safety. Throughout the process, strict safety protocols are enforced, including lockout procedures, PPE use, and careful handling of all components. Technicians monitor clearances and recheck alignments at every stage, confirming that tolerances meet precise requirements. Sensors and control devices are replaced if worn, guaranteeing accurate operation in the field. Feels like these machines are reborn, ready to power industrial systems reliably. The restored compressors often outperform original specifications after careful repair. By the end, the Howden screw compressor is fully restored, capable of delivering consistent pressure and airflow across multiple industrial applications, from chemical processing to HVAC and beyond. Somehow, the teamwork here makes heavy engineering look almost effortless. The repair process blends raw mechanical power with technical expertise, ensuring every machine leaving SCS performs to exacting standards. Seeing the compressor go from disassembled components to fully operational status is oddly satisfying in a way that makes mechanical work feel alive. Years of operational data are reviewed to ensure each repair matches expected performance. This combination of strength, skill, and precision ensures that industrial operations can rely on these restored compressors for years of dependable service. Every repaired compressor contributes to safer, more efficient industrial environments. BBCR transforms raw steel into bearings capable of handling extreme stress with precision. The steel begins as carefully selected billets, machined into inner and outer rings with exact tolerances. Rollers are formed and heat-treated to improve hardness and durability. Those tiny rollers hold more stress than you might imagine. Each component moves through automated grinding machines to achieve the final dimensions, maintaining concentricity critical to performance. Grinding tolerances are checked continuously to prevent deviations that could affect bearing lifespan. Lubrication grooves are cut into the rings, enhancing operational reliability. The assembly stage aligns inner and outer races with the tapered rollers, ensuring minimal friction and maximum load capacity. Every bearing undergoes visual and measurement inspections to catch even the slightest imperfection. Bearings are then tested under simulated operational loads, checking rotational smoothness and noise levels, guaranteeing each unit meets strict quality standards. Advanced coating techniques are applied to prevent corrosion, while packaging ensures protection during shipment. Throughout, Industry 4.0 monitoring provides real-time feedback on each machine's performance. That level of control feels almost like a well-orchestrated symphony of steel. The automated systems allow instant adjustments, reducing waste and downtime. Staff coordinate robot arms and conveyors, keeping production continuous without sacrificing quality. Final checks include dimensional verification, noise assessment, and lubrication verification before bearings leave the factory. Seeing how consistently each bearing is produced makes the whole operation feel incredibly efficient. From raw steel to finished, ready-to-install tapered roller bearings, every step highlights precision engineering and robust quality control that keeps industries moving worldwide. The combination of human expertise and automated monitoring creates reliability that industries depend on daily. Feel the sheer scale of operations at Olmsted County Waste-to-Energy Facility, OWEF, where every ton of waste gets a second life as energy. Conveyor systems move mixed refuse into hoppers, separating large items that could disrupt combustion. The sheer power in the sorting line makes it look unstoppable. Automated magnets pull ferrous metals aside, while non-combustibles like glass and stones are removed for recycling or landfill. The plant's engineers monitor each step to maximize energy yield without compromising safety. Next, the processed waste enters the combustion chamber, where high temperatures break down organic matter. Steam rises, driving turbines that generate electricity for the grid. Didn't expect a pile of trash to feed so much energy into homes. Heat recovery systems capture residual warmth, making the operation more efficient and environmentally conscious. Emissions pass through scrubbers and filters, ensuring pollutants are minimized before air is released. Hazardous components are identified and treated in specialized sections, protecting both staff and surrounding communities. Ash and other residues are separated. Metals are extracted for recycling, while mineral residues can be repurposed in construction. That pull before metals are sorted always looks like a controlled tug-of-war. Materials recovery areas handle plastics and paper unsuitable for combustion, adding another layer of sustainability. Educational programs run by the facility teach local residents how proper waste management contributes to energy production and environmental protection. Fuel derived from non-recyclable waste powers the turbines, providing a renewable energy source from material that would otherwise burden landfills. The integration of recycling, energy conversion, and community education showcases how an entire waste stream can be transformed into useful outputs. OWEF handles thousands of tons annually, producing electricity, reducing landfill volume, and extracting metals for reuse. Somehow the whole system keeps going smoothly, like a well-oiled giant. This facility proves that even what seems useless can serve an essential purpose when technology, planning, and human oversight work together. Cast aluminum is pushed and stretched at Koenig, yet the final wheel becomes stronger than before. The spinning inner barrel is pressed precisely, stretching and compressing the metal to boost tensile strength. This method creates wheels that are lighter yet tougher. That durability looks surprisingly confident for such a thin aluminum section. Ongoing tests ensure each wheel meets strict quality standards, with improved elongation and shock resistance, making every Koenig product ready to handle greater loads without compromise. Follow the slab as it glides along SMS group rollers, solidifying into steel perfection. Steel production at SMS Group for Puyang relies on the slab caster to form continuous slabs from molten metal. The caster's design ensures each slab has consistent thickness and minimal surface defects. The molten steel is carefully monitored as it enters the casting mold to ensure a uniform flow. Cooling water sprays over the slab, solidifying the outer layers while the inner core remains malleable. Operators focus on maintaining the perfect casting speed. Too fast or too slow could affect quality. As the slab moves along the caster, rollers guide it steadily, preventing warping or misalignment. Each slab is inspected visually and with sensors for defects or inconsistencies. Even small variations in mold alignment are corrected to prevent long-term issues. If adjustments are necessary, technicians tweak the mold or the cooling rate to maintain the correct dimensions. The integration of mechanical and electronic controls is remarkable in maintaining uniformity. Real-time control systems ensure that no detail goes unchecked during casting. Once the slab reaches the cutting section, automated shears slice it to the required lengths. These precise cuts ensure that each piece is ready for downstream rolling and processing. Following cutting, slabs are marked with identification codes, confirming their origin and specifications. Throughout casting, temperature probes, flow meters, and surface scanners continuously report data to ensure stability. Even minor temperature fluctuations are corrected in real time to maintain metallurgical properties. After leaving the caster, slabs are stacked and prepared for shipment or further processing. You can see why continuous monitoring and expert adjustments are crucial. One misstep could affect thousands of tons of steel. Every step in this SMS Group casting process demonstrates industrial precision, combining molten metal control, mechanical guidance, and careful quality checks. Even the seemingly simple act of moving a slab involves complex coordination between machinery and operators, ensuring that each slab meets rigorous standards before leaving Puyang. The level of synchronization here is surprisingly captivating, almost like a mechanical ballet. How does the Waldrich plano miller handle a 10 to 20 millimeters cut in high alloy steel so smoothly? Operators position the 2000 by 1200 millimeters plate before the R220.60 minus 8,315 cutter engages, using SPEN 2807 ZETRR 202.5 inserts. Rough face milling begins at 65 meters per minute, removing 10 to 20 millimeters per pass with 0.51 millimeters/tooth feed. The sheer stability of the machine keeps the plate perfectly flat under the high tensile forces of Impac's HH steel. That cutter seems hungrier than expected, chipping away the metal with no hesitation. The coordinated feed and rotation make every pass look effortless and powerful. The process continues across the full surface until the plate reaches precise flatness. Final inspection confirms consistent quality and surface finish. Feels like watching muscle and metal working in sync.
The hammers and presses don't just hit, they shape tools built to last. That spark from each strike almost feels like the metal is deciding its own shape. Operators position billets on the anvil, aligning them for precise forging. Hydraulic presses and mechanical hammers deliver controlled blows, gradually forming the steel. This is why industrial forging remains unmatched for strength and consistency. Blacksmiths rotate and reposition each piece, ensuring uniform thickness and proper angles. Temperature is carefully monitored to maintain optimal malleability, preventing cracks. In parallel, automated machinery assists with heavy lifting, reducing strain while maintaining speed. Each forged piece undergoes inspection, measuring dimensions and surface quality. The workflow looks deceptively simple, but it handles extreme force with finesse. Items are prepared for finishing, polishing, or assembly into larger components. The blend of human judgment and mechanical precision guarantees reliability in every product. Feels almost like the steel itself is cooperating with the team. Even complex shapes emerge efficiently under careful coordination. That combination of muscle, heat, and technique packs more power than you expect.
Operators at Skoda's test facility align the HCW 200s precisely to push its limits. The first power test runs at 66 kilowatts with a 160 millimeters cutting tool, reaching 250 meters per minute across 1,300 millimeters Z-axis. That pull looks stronger than expected for the first setup. Next, the machine ramps up to 100 kilowatts using a 200 millimeters cutter, maintaining stability at 185 meters per minute over the same travel. A final run tests a narrower 100 millimeters width while holding full power. Feels like this machine doesn't waste a second thinking. Observing the output demonstrates how working space is fully exploited. Can't believe how compact yet powerful this setup is. Gaze at the immense ITER vacuum vessel, a stainless steel fortress designed to contain the fusion reaction. Each of its 9 sectors towers 6.5 meters high, spans 3 meters wide, and measures 6.3 meters deep, weighing roughly 500 tons. That scale alone is jaw-dropping for a single sector. Europe is tasked with manufacturing 5 of these colossal sectors, and Walter Tosto's factory is where precision meets raw steel. Engineers perform thorough welding and dimensional checks in pristine clean rooms. Seeing these sectors take shape under strict tolerances is something else. Teams from F4E and Saldo Nucleare, Mangiarotti, and Walter Tosto coordinate every move, ensuring each sector aligns perfectly. Feels like controlled power in motion inside the factory.
From drilling to welding, each reactor vessel component undergoes precision operations at the Saint-Marcel plant in Bourgogne. The sheer size of the lifting systems can make you blink twice, 50 to 600 tons handled with smooth precision. Tubular plates move through drilling and machining stations, inspected at every stage to maintain strict tolerances. Automated inconel coating ensures corrosion resistance under extreme heat and pressure. Welding combines automatic precision on vie rolls with skilled manual work for critical joints. Elliptical steam generator bottoms are shaped and finished using advanced digital workstations like NEO3D. Each component passes hydraulic testing, confirming safety under operational stress. Assembly continues in heavy bays, with hoists handling up to 600 tons, while staff coordinate complex sequences of machining, coating, and welding. The integration of digital monitoring and human expertise keeps production flawless across hundreds of tons of metal. Final inspection verifies dimensions, coatings, and weld quality, preparing each steam generator for deployment at Hinkley Point or replacements in the French nuclear fleet.
Giant steam boilers take shape at EKOL's Brno facility, engineered to power energy plants around the globe. It's fascinating to see how every massive metal cylinder is aligned with the control systems before assembly. The team first positions each boiler frame precisely, ensuring structural integrity and safety for high-pressure operation. Piping modules are then added, connecting the boilers to EKOL's custom-designed turbines. The coordination between engineers and technicians here is surprisingly fluid, almost like a well-rehearsed ballet. Every weld and joint undergoes rigorous inspection, making sure the steam will flow efficiently without leaks. Next, the control panels are integrated, allowing operators to manage the flow, pressure, and output of the system. You'd be amazed at how compact these control units are considering the power they regulate. Once the assembly is complete, the boilers are tested under simulated operational conditions. Sensors measure temperature, pressure, and efficiency, while technicians adjust valves to fine-tune performance. That pull on the turbines looks stronger than expected, almost like the system could handle a small industrial town. Finally, the fully equipped boiler is prepared for shipment to its destination, whether powering Nile Sugar's energy center in Egypt or another facility worldwide. Didn't expect these components to fit together so seamlessly. It's kind of satisfying to see the raw metal evolve into a fully functioning energy unit. Hundreds of upgraded components come together as Siemens Energy refines the ATEP package for the SGT5-4000F gas turbines, focusing entirely on higher efficiency. The team begins by assembling the newly designed turbine section, shaping fresh aerodynamic geometry for better flow. That redesign feels like pure intent in metal. Testing crews then install dense arrays of temperature, pressure, and vibration sensors to verify real behavior under load. Feels like the blades are ready to show what they can really do. Field teams coordinate replacements, align instrumentation, and confirm performance gains that help plants deliver more power with less fuel. Good fabs, mandrel bender shapes inconel tubes into flawless exhaust curves. The setup process demands careful positioning of each die, mandrel, and support rollers to prevent tube collapse or wall thinning. Once secured, the operator adjusts the hydraulic pressure and rotation speed for optimal bending force. Feels like controlling a beast with exacting finesse. The first tube is clamped and the mandrel is inserted, moving inside to support the tube throughout the bend. Every millimeter of adjustment matters to preserve the inconel's integrity. The machine gradually curves the tube along the intended path, maintaining uniform diameter. You wouldn't expect this hard metal to flex so smoothly. Bending angles are verified continuously, and micro-corrections are made to avoid kinks or ovalization. The exactness of that final curve almost feels alive, bending without a fight. After the bend, the tube is released and inspected with precision gauges. Titanium and stainless steel tubes follow the same careful routine, requiring tailored mandrel positioning and pressure. That setup looks deceptively simple, but it's pure mechanical skill and engineering at work. Final trimming and welding complete the exhaust assembly, ready for Formula One teams. Steel strips move through JSW Steel's Pickling line tandem cold mill, engineered to produce high-quality strips for demanding industrial applications. The coil preparation system handles a massive variety of steel grades, from IF to trip, ensuring versatility in production. At the coil preparation station, operators carefully position massive coils on the carrier roller table, making sure the lower strand aligns perfectly with the 7-roll pre-leveler. Swingable triple support arms guide the upper strands while maintaining consistent tension across more than 700 meters of strip. Each movement is synchronized, allowing the coil to feed smoothly into the turbulence pickling section, which includes 3 tanks of 35 meters each. Here, scale and impurities are removed at a maximal pickling speed of 300 meters per minute. The scrapper units almost make it look like the steel is getting a fresh haircut. Recuperator tanks recycle pickling solutions to save chemicals and reduce environmental impact. After pickling, strips pass through the 5-stage cascade rinsing system, followed by the strip dryer and intermediate looper. Inline water management systems maintain optimal rinse efficiency while minimizing resource use. The combined ASC side trimmer, equipped with scrap chopper and burr masher units, ensures precise trimming. Those knives swap faster than expected, making a large-scale operation seem almost effortless. The exit looper and bridle rolls stabilize tension before the strip enters the high-performance tandem cold mill. With 5 stands featuring CVCO Plus ESS technology, work and intermediate roll bending, multi-zone cooling, and a dry strip system, the mill reduces thickness from 1.50 to 6.50 millimeters down to 0.30 to 2.60 millimeters, achieving rolling speeds up to 450 meters per minute. At the continuous exit section, inline thickness and flatness measurement systems verify quality, followed by a powerful drum shear and rotary inspection. Coils weighing up to 50 tons are wound onto the compact carousel reel. That pull on the coil is stronger than you'd imagine for its size. The production line integrates a fume exhaust system, an emulsion plant with efficient filters, a vacuum filter system, and a chain-type magnetic separator to maintain sustainability. Kind of funny how the steel seems to float effortlessly through each stage. Every step ensures JSW Steel meets strict customer requirements, producing resource-efficient steel strips suitable for automotive, construction, and specialized engineering applications. Operators monitor each stage closely, adjusting roll bending and tension control to guarantee consistent flatness. The combination of high-speed tandem mills and automated inspection makes it feel like the steel is racing against precision itself. From coil loading to compact reel winding, the line blends advanced technology with engineering expertise, maintaining quality across a wide range of steel grades, including HSS, BH, DP, CP, HSLA, and trip steels. Coupling precision measurement with fast coil handling maximizes throughput while keeping defect rates low. Follow the robot's torch as it glides across the Overhaul, welding each joint with precise motion. Every aluminum bolt moves into position under the TDRI fully automated welding cell, guided by programmed robotic arms. The scene-finding cameras scan each panel with precision, adjusting the weld path in real time to match every contour. This system
Operators and rolling machines at Tranecki Zelezarny collaborate to produce strong, reliable steel. Raw iron is first processed in blast furnaces to reduce impurities and reach optimal composition. That push of molten iron into molds has more force than you'd expect for such precise control. Continuous casting transforms the molten material into slabs, which are then cooled and inspected for structural consistency. Rolling mills shape the slabs into sheets and beams, compressing and elongating steel while ensuring uniform strength. The coordination between operators and rolling machines looks almost like a complex puzzle being solved in real time. Next, sheets and beams pass through heat treatment, altering their internal structure to enhance hardness and flexibility. Grinding and finishing lines smooth surfaces, preparing the steel for industrial applications. Refractory-resistant areas handle high-temperature operations, while safety teams monitor emissions and equipment stress. Never thought the metal could hold up so well after all this pressure. Automated inspection systems catch flaws early, maintaining product quality without slowing production. Finally, finished steel is sorted, packaged, and dispatched to construction, manufacturing, and energy sectors. Somehow, all these massive steps come together like a well-rehearsed machine orchestra. Operators and CNC machines interact seamlessly at 1D Auto Parts in Xiamen, shaping raw steel tubes into axles built to endure the heaviest loads. The synergy between man and machine here really defines industrial efficiency. Cutting these tubes to precise lengths is crucial. Every millimeter matters. The tubes go through CNC spinning forming to shape them into uniform beams, followed by CNC cold pushing to create square beams with reinforced structure. CNC quenching and tempering improve hardness and durability, making these axles reliable under heavy loads. Heat treatment consistency ensures the beams won't bend under extreme pressure. Seeing the beams move through these heat treatments is kind of intense. Both ends are cut, and the axle beams are straightened before entering the fully automatic primer painting line for corrosion protection. Machining follows, starting with dedicated CNC lathes, then keyway milling, split pinhole drilling, and precision grinding. Each milling cut and drilled hole directly affects axle lifespan. Each beam undergoes size accuracy inspection and coordinate accuracy detection to meet stringent dimensional requirements. Automatic weighing or brake shoe bracket fitting using special tools ensures uniformity, while double-side 3-hole boring lathes maintain 4-axis parallelism. Camshaft support welding and automatic air chamber bracket welding are next, followed by camshaft assembly. The fully automatic painting line finishes the assembled beams, which then move to warehousing. Wheel hubs and bearings lubricated with mobile grease are assembled, and hubs with brake drums are combined. Automatic painting lines, coat hubs, drums, and brake shoes. Axle assembly lines integrate axle parts, brake drums, hubs, camshafts, and slack adjusters. All axles meet JTT 475-2-002, TS 16949, and ISO 9001 standards, passing third-party laboratory certification. Warehousing, container loading, and marine transportation complete the production cycle, delivering axles to customers worldwide. The careful inspection at multiple stages guarantees customers get reliable axles. From raw, seamless tubes to fully tested and painted axles, each step highlights precise engineering and quality management. Custom axle beams and parts are available to meet diverse client requirements, ensuring every delivery is up to standard. Every single axle leaving this factory carries the assurance of consistent performance.
Giant wheel sets designed for high-speed rail operations are carefully handled at Gemini's facilities. Operators position each wheel set onto the machining platform, using hydraulic lifts and clamps to stabilize the massive components. That torque doing the talking here. These wheels are heavier than expected. The first task in the assembly sequence aligns axles precisely with the spindle, ensuring perfect rotational balance. CNC machines then begin the machining process, cutting and refining surfaces for seamless wheel-rail contact. Sensors continuously monitor tolerances to maintain strict specifications. You'd never guess that rough steel could be smooth so quickly. Technicians guide the wheel sets through multiple operations, including flange profiling and hump finishing, confirming that each cut meets design standards. Hydraulic actuators adjust positions in real time, allowing smooth, controlled passes. Feels like this machine doesn't waste a second thinking. After machining, operators remove clamps and transfer wheel sets to final inspection stations, checking roundness, dimensions, and bearing fits. Once approved, the GR7S wheel sets are ready for integration into rail cars. This setup feels like precision and raw strength working side by side. Throughout the process, human oversight and automated machinery coordinate seamlessly, delivering wheel sets that combine durability, accuracy, and reliability for high-speed rail operations.
Sheets feed smoothly into the Sente Machina 2mm auto self-flanged duct former. That curl at the edge looks oddly controlled. Elin Motor GmbH produces electric motors designed for exceptional durability and efficiency. That torque capacity looks bigger than expected. Workers monitor coils closely, ensuring each motor meets stringent standards. Aluminum rotors are fed precisely into the NI-D automatic armature rotor die casting machine designed to optimize efficiency while minimizing labor. That speed alone could catch anyone off guard the first time. Once secured, molten aluminum fills the mold uniformly, forming each rotor with consistent density. Cooling cycles follow, ensuring durability without compromising shape. You can almost feel the torque potential packed into these rotors. Ejection mechanisms then remove the finished pieces carefully to prevent damage. The system repeats continuously, balancing power saving and high throughput. Operators monitor sensors and control panels, adjusting parameters as needed. That stream of finished rotors rolling out looks oddly satisfying in an industrial way. With NIDE's design, health and safety are prioritized, labor costs reduced, and production is steady. Every rotor demonstrates precise control over temperature, flow, and cycle timing. This setup feels like muscle and intelligence packed together. Industria's FC uses StackTech 5-piece collapsible cores to mold cream jars with 360-degree internal negatives. Collapsing cores prevent stretching defects. Engineers verify cavity alignment and wall thickness. This precise control enables designs impossible with traditional injection blow or extrusion blow methods.
Metal rods move through the Revax Machinis MEC5 and MEC8, straightened and cut with impressive plus or minus 0.1 millimeters accuracy. CNC programming adjusts measurements instantly without guide changes. MEC5 handles rods up to 5 millimeters. MEC8 up to 8 millimeters. The speed and control make it almost hypnotic to watch.
Over 85,000 square feet of Buddy Bar's foundry hum with activity, each station producing precision aluminum castings at impressive scale. Setup of the core machines includes verifying alignment tolerances within a fraction of a millimeter. Operators first set up the core machines, aligning dies and mandrels on 20 automatic core machines and the AEMPE ISO core system, ensuring each mold meets tight tolerances. Quality raw materials are measured and assembled into cores, which are then inserted into dry sand molds. It's surprising how structured sand can guide molten metal so reliably. The molds proceed to the green sand production lines, passing through sand reclaimers and the thermal sand reclamation system, recycling 100% of the sand while maintaining strength and consistency. That reclaimed sand works harder than most materials in the factory. Once prepared, aluminum is melted in one of 6 furnaces, each capable of 500 pounds per hour, and poured into the automated match plate molds. That molten metal seems eager to fill every crevice of the molds. After solidification, pneumatic shakeouts release the castings, which then enter a 6-axis robotic deburring cell. Wheelabrators finish the surface, smoothing edges and preparing components for final machining. Robots handle every angle with uncanny steadiness, almost like the castings are learning their own shape. Casting weights and dimensions are checked before moving to finishing. After solidification, pneumatic shakeouts release the castings, which then enter a 6-axis robotic deburring cell. Finally, complex aluminum castings move to the machine shop, where precision machining ensures every part meets stringent engineering standards. The sequence from raw material to finished casting is thorough, yet flows with remarkable efficiency. Each stage, from core assembly to finishing, combines human expertise with advanced machinery for consistent, high-quality output. Every component is logged and tracked for traceability and quality control. Even minor imperfections are flagged for corrective action before final release. Feel the immense power of Macquarie Engineering Limited S600-ton, 7-meter EHT Truband, the largest single-span press brake in the country. The lifting aids integrated into the machine make handling large metal sheets almost effortless. Operators slide each steel plate onto the bed, aligning it precisely with the bending dies to ensure exact angles. With every press, the hydraulic system pushes the ram downward, folding the metal cleanly while maintaining structural integrity. Even thick, high-strength plates bend smoothly without any need for multiple passes. The flexibility of the press brake allows for rapid adjustment between jobs, accommodating a wide range of sheet sizes. Watching the metal yield under such controlled force shows the engineering precision packed into the Truband. Once the bend is complete, the operators inspect angles and edges before moving the workpiece to the next stage. The speed at which this giant machine completes complex bends is surprising for its sheer scale. From start to finish, every operation emphasizes efficiency and safety. It's impressive how the combination of hydraulic power and precise alignment makes heavy-duty bending appear almost simple. Short runs or large panels, this press brake tackles them all with confidence. That moment when the metal bends perfectly in a single press feels oddly satisfying. The NIDE Group's fully automated EV motor stator line operates with remarkable coordination and high efficiency. The manipulator arms glide with precision, almost like a conductor leading an orchestra. They feed cores with exceptional accuracy, reducing human handling and potential errors. Each stator undergoes QR code scanning at the beginning to ensure traceability and correct processing for every component. It's fun to think that a tiny code can control such a big operation. Slot insulation paper is inserted with exact positioning, forming the foundation for reliable electrical performance. Each sheet is positioned like a puzzle piece, locking perfectly into place. At the first insertion station, coil alignment is verified mechanically, making automation feel surprisingly clever. Coil winding and insertion then follow, with preforming operations shaping the coils perfectly to fit into the stator slots. Preforming guarantees that the coil won't fight against the slot later. Phase paper insertion and star spot welding reinforce electrical isolation and structural stability. Even minor misalignments are caught immediately by the sensors, saving hours of potential rework. The multiple stations operate in harmony, producing high throughput without bottlenecks. Middle forming, double-sided lacing, and final forming refine coil geometry and tension. The lacing machines move almost like robotic fingers tying precise knots. Terminal installation and welding complete electrical connectivity, preparing the stator for testing. Automated inspection stations catch slight deviations immediately, saving time and avoiding defective outputs. Stators that pass proceed to unloading, while NG rework handles those needing adjustments. Artificial alignment and expansion stations guarantee that each coil sits correctly within its slot. Mechanical feeding complements manual wiring and tooling installation where human precision is required. The interplay between robots and human skill keeps quality consistently high. Star welding adds structural integrity, and fine shaping ensures tolerances are maintained. Double-sided lacing secures the coils, while terminal welding finalizes electrical connections. The system switches between production modes within just 2 hours, enabling flexibility for different EV stator types. It's impressive how quickly the line adapts to a new stator design. Slot expansion prepares stators for final inspection, where operators confirm alignment and slot integrity. Manipulator feeding, QR scanning, paper insertion, coil winding, preforming, star welding, middle forming, double-sided lacing, terminal welding, slot expansion, and final inspection collectively ensure high-quality stators. Even large production batches move efficiently, showcasing effective automation and process design. The line demonstrates intellectualized, automatic, and informational manufacturing, combining robotics with process intelligence.